Hello and welcome to Talking Points. I'm Dave Kelly, Director of Advanced Media Production at Cal State Long Beach. Today we're going to talk about the Miocene Monterey Formation, also known as the Monterey Shale Formation because that's where most of California's oil and natural gas resources reside. My guest today is Dr. Richard Bell. Dr. Bell is a professor of geological sciences. Thank you for joining us, Rick, on Talking Points.
It's my pleasure, Dave.
Well, let's give our audience a sense of, in the broader scope of things, what the Monterey Formation is all about. I know that it was formed somewhere between 17.5 million years ago to 5 million years ago, so there's about a 12 million year stretch there where those sediments were deposited along with the aquatic life. What else can you tell us about its characteristics and why is it geologically significant?
Well, in California, it's actually part of a broad band that goes all the way around the Pacific Rim, and it actually marks or records a tremendous change in past climate and ocean circulation. And that change has brought a lot of nutrients to California and created a vast amount of life, which was ultimately deposited on the sea floor, and that life is made up of the tiny shells and organic matter from the ocean plankton.
And when we talk about shale, that's where we're now finding a lot of the oil resources.
Yeah, so shales are fine-grained rocks or made up of mud-sized particles, and these tend to be the most organic-rich rocks and sediments deposited on Earth. And so these have always been considered the source of oil, that where the organic matter accumulates, and then with burial it cooks itself into oil, and then that oil migrates out into other kinds of rocks that trap it. But in this particular case, in the last 10 years, we've been finding out how to get the oil out of those source rocks directly rather than having to wait for it to go into other places.
And we're going to talk about that in a moment. That's called hydraulic fracturing or fracking.
That's one of the techniques used to get it out.
And before we get to that, let's give our viewers some visuals. You've brought in some wonderful, very colorful slides today to give our viewers a good sense of visually what this represents. So let's take a look at our first slide. What are we looking at here?
Well, this is a map of the distribution of the Monterey Shale on land in California. It's simplified in that it doesn't show all the variation, and it doesn't really show all the stuff going on offshore, but you can see that it's very broadly distributed along the coast and in the central southern part of California.
And we know that in the San Joaquin Valley, in the basin there around Bakersfield and Kern County, that's where we get a lot of our oil, and we've been extracting oil from that area for about 100 years or more.
That's right. Most of our oil production is from the southern San Joaquin Valley, but we also have a tremendous amount in Los Angeles and Santa Barbara, Ventura areas.
Okay, let's go to the next slide. What are we looking at here, Rick?
Well, as you drive around California on the coast or through the mountains, you'll often see these light-colored, thinly layered rocks. These are the Monterey Shale. They have this light color because they're very porous and they have been weathered by water and oxygen, but actually down in the subsurface when they're fresh, they're a dark, rich brown.
And you see some interesting vertical striations there in that slide.
Yeah, well, that's the layering. Those are the original sedimentary layers that occurred over time.
All right, let's take a look at the next image. What are we looking at here?
Well, this is in the San Joaquin Valley on the edge of it in the Temblor Range, and this is a particularly silica-rich portion of the Monterey Shale that was originally made up of diatoms, single-celled planktons in the ocean that have now been converted into harder, more brittle rocks.
And in the next slide, we can see what I have a very vivid imagination. So to me, this looks like a series of surfboards that have become petrified, planted by cavemen years ago.
I like that story. This is what the Monterey Formation looks like a lot of places where it's freshly scrubbed by the waves and sand. And you can see the layerings of the dark black, very organic rich shale and the lighter colored surfboards of yours that are more brittle and harder layers.
And if we go to the next slide, we can see where the coastal influence is clearly there. I mean, it looks like some tide pool activity.
Yeah, well, we do a lot of our work along the coast because the wave action cleans the rock so well. It gives us fresh surfaces to study. And here you're starting to see a little bit of the folding that is so common in the Monterey.
And if we go to the next one, we can see this is in Southern California, not far from here, but there's some interesting formations there, and again, the tide pool influence.
Yeah, these are concretions in the Monterey and Crystal Cove State Park, Sometimes we call them hamburger buns or flying saucer concretions. And these nucleated and grew around driftwood that settled to the bottom in this area from ancient floods.
And I know that bone material and bone mass sometimes occurs. Let's go to the next slide and take a look at that. What do we have here?
Yeah, well, so most of the Monterey sediments are made up of microscopic shells of little plankton that was floated in the ocean, but there's a lot of really excellent preservation of macroscopic or large fossils, and this is a whale vertebra. And the Monterey Formation, because it was deposited in an area without oxygen and most of the bones were not chewed up on by anything else, has some of the best collections of large fossils in the world for this time.
If we go to the next slide, we see some researchers doing some studies here.
That's right. This is a class visit actually out where they're studying the orientation and size of fractures that occur in these rocks from tectonic activity.
Next slide, please. There we see a vertical lift of striation.
Yeah, this is a cliff behind a beach, and you're starting to see the much more intense folding that is common in the Monterey because of the past earthquakes and crustal movement.
And on our next slide, we see some scale with the folks standing in front.
All right, this is a outcrop near Lompoc in Santa Barbara County, and this is the kind of deformation that both starts to fracture the rocks and also fold it into large structures that act as traps for oil and gas underneath the surface of the earth.
And the next slide looks like, again, my vivid imagination is kicked in here. That looks like the caramel swirl ice cream I get at the grocery store.
Yeah, this is a lot like that. It's been swirled too, but it's been by natural forces, and you're seeing the black and white cherts, which are actually highly fractured, and then the orange dolomites, and the rocks have been folded so much that they then fractured and broke right on through with that fault.
Let's go to the next slide.
Actually, another view of a similar area along the coast. So as you see, we do a lot of our work on the coast just because the exposures are so excellent.
And the next slide shows that petroleum is part of the makeup here.
Well, this are actually fractures called normal faults, which are a kind of a fault that occurs when you pull the rocks apart. And they look almost like a bunch of books on a bookshelf that are toppling over if you took the book's end away and they were able to fall down.
Mm-hmm. Okay, next slide, please.
So this is looking down on a wave-cut beach platform up near Morro Bay, and you can see the layers, the thin layers of rock, but what's of note here is these large fractures cutting through 50, 60, 80 feet of rock. These are natural fractures that we come out to study in this area.
And we've got another slide coming up here that is more of a close-up view of that.
Yeah, exactly. This is a close-up of the intense fracturing that occurs in these rocks naturally. And this is very important for letting fluids of all type move through these rocks: water, oil, gas.
So they're very porous, as you mentioned earlier.
Well, the rocks themselves, some of them are porous and others are not, but these fractures are critically important to be sort of the pipes that let lots of fluids move through them.
Entry points, yeah.
Yeah.
Okay, if we go to the next slide, there the oil is obvious in those darker areas.
That's right. This is what we call a breccia, which is where the rock's been so fractured that it's been broken up into tiny little angular pieces. And as you say, all the black there between the orange fragments is actually heavy oil, almost a tar.
And if we go to the next slide, what are we looking at there?
Well, this is showing how the interlayering of the different kinds of rocks is so important. The light-colored layers are more brittle, more what we call a chert, and they're highly fractured. And the browner layers are a shale, and they have more clay in them, so they're a little bit more squishy and deformable, and they don't fracture the same way.
Okay, if we go to the next slide, we have a nice view of some oil actually oozing out of the ground there.
It is. This is a natural seep coming up along that fracture that you see at the bottom of the screen and then oozing out on the surface, and it flows particularly rapidly on hot days when this thick, heavy oil loosens up a bit.
And on the next slide, we see a close-up there as well.
Another case of the same kind of thing, oil working its way up through fractured rocks, and this is how the oil industry really started in California over 100 years ago, is the discovery of these natural seeps all through California.
And the next slide gives us a microscopic view.
Yeah, this is almost a microscopic view of thin little layers that are only about 1 millimeter thick, and even those you can see are intensely fractured. So that's what happens when you live in California.
And in the next image, what are we looking at there?
Well, this is a nice picture of the weathering of a limestone in the Monterey Formation, where you see these beautiful patterns that look a lot like you find in a Chinese rock garden.
And let's look at our last slide here, and that shows the kind of good fortune you have to be in this profession.
It sure does, and this is what actually brings a lot of our students in the first place. If they love the outdoors and they want to understand why things are the way they are, and they get to go out and work in places like this, it's not really a hard sell.
Absolutely. So, Rick, when we talk about oil extraction through these areas that we're talking about as a shale formation, how is this different from the shale formations that we're talking about in North Dakota these days?
Well, first of all, oil's been taken out of California for over 100 years, and the Monterey Formation is the source of most of that oil. It had the organic matter that turned into oil, but in the past, that oil, after it was formed, worked its way up into either other rocks or other part of the fractured Monterey, where we extracted it without any fancy techniques. But these other shales have, in North Dakota and Texas and Ohio, New York, are not fractured like ours are here in California. And so they had to develop new techniques in order to get that oil out of them. But in other ways, they're similar to the Monterey, but they're not in California, so they don't have these natural fractures in them.
And I think there's also a lot more variation here in California in terms of where the oil is deposited in the geological formations than there is in, say, the Bakken Field in North Dakota.
Yeah, absolutely. You thought diversity was a new idea, huh? No, California
it's
has.
age-old.
Yes, it is. It really is. California has a huge variety in how thick the formation is and what its character is and how intensely deformed it is as you go from place to place, because it's a much more complicated area geologically than areas like in North Dakota, where you can go for hundreds and hundreds of miles with just minor changes in the layers, composition, and thickness.
Rick, we've come to the midpoint now, so we're going to have to take a break. When we come back, we'll talk more about California's oil extraction and where we're headed in the future. Stay with us.
You always made sure I brushed my teeth.
You told me that smart was cool.
You always told me to dream big.
To all of those parents who took the time to make raising their children their most important job, we'd like to say,
Thank you.
Thank you.
From the bottom of my heart, thanks, Mom and Dad.
This message is brought to you by the U.S. Air Force.
Hello and welcome back to Talking Points. I'm Dave Kelly, and my guest today is Dr. Richard Bell. He's a professor of geological sciences. And Rick, when we went to the break, we started to talk about comparisons between the Monterey Shale Formation and the Bakken Field in North Dakota, and also we brought up the Texas Eagle Ford and some of the other fields that are out there. When we talk about fracking, hydraulic fracturing, it's raised a lot of controversy of late, but I think what people don't always realize is that it's been around for a good 3 or 4 decades here in California, and other folks who are involved in this issue may not realize that we actually fracked about 600 wells, according to the statistics I read, in 2011 alone. What can you tell us about fracking?
Well, hydraulic fracturing is a technique to help get more oil and gas out of rocks that are otherwise too tight or have too low permeability to have the fluids or gas come out of them. And so it's not a drilling technique. It's, as you said, it's been around for more than 40 years. The difference, and I think the reason why it's become an issue is twofold. One is, and you actually mentioned it there for a second, is that prior to the last 10 years, oil and gas production was from fields, localized areas where the oil had moved up from the source rocks and accumulated in small areas, and they were able to drill into and get the oil out of them. Now that we've discovered we can get oil out of those original source rocks, with these extra techniques, we're expanding out of areas that were traditional fields. And so they're going into much larger areas that didn't have oil and gas development before. So you're having this face-to-face interaction of people with a big industry and an industrial process they haven't seen before. So hydraulic fracturing is one of a couple methods that are important for getting oil and gas out of these tight shales. And it's simply that after you drill the well, you take a part of the hole, you isolate it, you pump fluids of high pressure that also have sand in them and some polymer to keep the sand suspended hard enough that it cracks the rock. It shoots the sand into the cracks so they can't close back down again, and it gives much larger surface area for the oil and gas to seep into the well from. And then they move it a little bit farther and they do that again, they do that again. So now they're doing what they call multi-stage fracturing, which allows them to make fractures all along the well bore while it's in the interval that they're interested in getting the oil and gas from.
Well, one of the main concerns is that by doing this injection of water and sand and some chemicals underground, that we might be contaminating the water table, the underground water table. Is that fear a rational fear, or is that maybe not as rational as has been presented?
Well, the concern is completely valid. Okay, I mean, water supply, pollution, all these things are important things that we as society want to control and regulate. And so there's nothing at all wrong with that. It's not anywhere near the issue that a lot of people think it is, though, and that's for a whole variety of reasons. And one of the reasons is that when you drill a oil well, you drill a small part, usually a few hundred feet, and then you put in a steel casing, we call it. You cement it into place, and then you drill inside of that deeper, and you put another steel casing, you cement that in place, and that's purpose is to completely isolate the aquifer where the water is that we may be getting groundwater out of from any deeper layers. And then they drill farther down into the zones that they are interested in getting oil and gas in. So in most cases, the separation of a zone that would be fractured and that may have oil and gas in it from water that's drinking water is many, many thousands of feet. And it's a huge distance that there's no evidence of, and there's no reasonable reason to think that they would cross-communicate. There are a small percent, like probably down in 1 or 2%, where the depth of the target zone for the oil and gas is close to an aquifer, enough that it needs to be seriously looked at to see what kind of regulations or even prohibitions need to be done for those particular areas. The more likely pollution of water supplies, I think, is not from the well and not from the fracturing, but is from bad practices at the surface, spilling of fluids and chemicals and things that seep down into the water table rather than coming up from the fractures. And that's the same kind of pollution that we get from runoff of roads, that we get from agricultural runoff of pesticides and all kinds of things like that as well. It's coming in from the top, and that needs to be regulated and done with best practices.
So stewardship is important. We don't want to gloss over that. We only have one planet, we only have one ecosystem and one environment, so we want to protect it. But we also want to be trusting the science in this case in terms of what you were just talking about in regard to the depth of the drilling and where the practical applications occur and what are the real fears and threats. As far as the re-injection wells, I know that they have to re-inject some water back into the ground in a lot of places. What about the re-injection wells? Are those a concern?
So, okay, so to give you a little information on that, when they do fracture these rocks, hydraulically fracture rocks, they use water. This is one of the issues of it. Luckily for us here in California, because we don't do the kind of long horizontal wells that use a lot of fracturing that they do in North Dakota and other places like that, we use about 1/10 to 1/20 of the water that they use in those wells. So we don't use anywhere near as much water in this. But in any case, when you do that, you fracture the rocks, and then when you start producing the oil and gas, water comes back. That's a wastewater. In some cases, that can be reused, but in other cases, the natural chemicals that are already existing in the water, in the rocks in the first place, cause so much of a change to the chemistry of the water that it's not usable to refracture again in another well. So the water has to be disposed of. So in those places, they have all this water they have to do something with, and it's not something you leave around on the surface. So they re-inject it in deep wells. In places like Oklahoma and Colorado, these are deep wells that go way down below the formations they're producing from. And they have some issues with those about the water injection and whether it's linked to any kind of induced seismicity as well. Here in California, we have been re-injecting wastewater on a massive scale for a very long time. The oil fields that you're familiar with here, right here in Long Beach, like the Wilmington field, is basically a water pumping operation. It takes out water with a tiny amount of oil, skims off that oil, and re-injects the water. We have injected vast amounts of water, and as you know, that there's a reason for that.
Right, and that is the subsidence issue that we had here in Long Beach back in the 40s when we were drilling out of the harbor in massive quantities during World War II. But in the late 40s, we started to see the land subsiding or sinking, and we were actually, Long Beach was called the sinking city for a few years there, and finally, and got to the point where the U.S. Navy decided to close the Navy shipyard because of the subsidence problem, but then the Korean War started, so they reopened it and said, well, we'll figure out the subsidence problem later. But we did come up with a solution for that, and it involves the reinjection that you're talking about.
Yeah, that's right. So one thing about the California geology and oil fields is, just like everything in California, it's young. Compared to the rest of the world, it's young. Our sediments and sedimentary rocks are vastly younger than other rocks. They have not been as deeply buried. They haven't been as compacted or cemented. So when you take out the water or the oil that's in between the grains of sandstones and things like that, the grains settle down and they rearrange, they compact. And so when you have a big column of thousands of feet that compacts a little bit, that means the surface goes down. And so in some places, like right along the coast where we are, that actually allowed the ocean to come on in, and that was the problem of subsidence. So what they learned how to do in the 70s pretty much was they learned to take all the water that came out, plus even some more seawater, and re-inject it enough that they stopped the subsidence and they actually reinflated the earth a little bit and recovered some of the land that had been lost to subsidence.
I call it subsidence, you call it subsidence. I guess by any of their means, the substance is the same.
That's right.
But in any event, the seismic activity, we have a lot of earthquakes here, obviously, in California. So is fracking contributing to that in any measurable way that you can discern?
There's been a lot of studies of that. And as far as I know, there's no studies that fracking itself directly has caused any earthquakes or helped any earthquakes occur. There is evidence in some other parts of North America that those deep injection wells that go down into very, very hard and deep basement rocks, well below the producing rocks that are coming from, have contributed to swarms of earthquakes. Most of these earthquakes are way smaller than a human being can even feel, but sometimes they're not, and they're enough to feel. Now, for us Californians, that's what they felt is not very much, but for people that aren't used to earthquakes, this was a serious issue. And so those injection wells have to be thought out carefully, where they put the water, how much water they put down them, because of causing this level of earthquakes that people aren't used to in these other parts of the country.
Okay, well, we're looking at a really sizable energy boom now in the United States because of all this fracking and also the horizontal drilling, which was also actually invented here in Long Beach. They called it slant drilling during World War II when they would go in under the harbor area with slant drills. But in any event, we're in an energy boom across the country now. We've increased our oil production by about 44%, I think, since 2005. Is this boom going to be around for a while? In 30 years, if we reconvene this conversation, don't count on it, I don't think I'll be able to be here, but if we were to have this same conversation 30 years from now, would we still be talking about this energy boom in California and the rest of the country?
You know, I think there's a good chance that it will be going on that long or longer. It's not going to go on forever, but but the new technologies allow us to get oil and gas out of rocks we couldn't get before, and those are actually the biggest accumulations. So I think it's going to go on for a while, and it's already made some pretty dramatic changes in the United States in terms of our balance of imports and exports of oil and gas, and amazingly and completely unintentionally in our greenhouse gas production. So because of this discovery and ability to get tremendous amounts of natural gas has become so cheap that many power plants that were getting their energy from burning coal, dirty coal, have switched over to natural gas, and our greenhouse gas emissions in the United States have dropped down to lower levels than they were 20 years ago.
Okay, Rick, we're almost out of time. We've only got about a minute left, so in 30 seconds or so, tell us about the Mars project you're involved in. I know it's not studying the images from the Mars probe, but what is the Mars project?
No, it's a bit of a tongue-in-cheek pun, but it's the Monterey and related sediments. It's a project we have here on campus in which I have about 10 graduate students that I'm supporting to do research on the Monterey Formation, plus about 4 or 5 undergraduate students. It's a very successful program that's allowed me to pay salaries to all these students and pay for all the research costs, so they're able to actually get through and do really nice master's theses in 2 years or so, which is quite an achievement.
That sounds like a terrific opportunity, and thank you for being with us today, Rick.
It's my pleasure, Dave.
And thank you for joining us for this edition of Talking Points. Join us for another episode soon. Until then, I'm Dave Kelly. Have a nice day.